Welcome to section 3, Thread Synchronization Primitives. In this section, we will learn about various thread synchronization primitives in Python and how to use these synchronization primitives in a multi-threaded application to prevent data corruption. We shall then look into the classic producer-consumer problem, how the standard Python module queue helps us handle the producer and consumer problem easily, and then we shall end this section with a note on why multi-threading is important in GUI programming. Synchronization in Python. In this video, we are going to look into the thread synchronization big picture. What is it and why is it actually required? Then we shall talk about various synchronization primitives available in Python. As we go through these primitives, we shall also learn how and when to use these primitives. So let's get rolling. In any multi-threaded application, there are always multiple threads that would access shared data. For example, a shared variable, or they can access a shared resource. For example, in such cases, if sufficient care and protection are not used, there is often a chance for data corruption or other inconsistencies, such as threads ending up using stale data. Using synchronization primitives, multi-threaded applications can intelligently get around such scenarios. Depending on the scenario, multi-threaded applications can choose a synchronization primitive to help application achieve its goal without any side effects. Let us take the example that we looked at in the last section, where multiple threads were fetching contents of different URLs and writing onto distinct files. Now, let us say if all of them have to write the contents they fetched onto the same file. Since the file becomes a shared resource here, if multiple threads try to write contents into it, they might end up having overlapping data from multiple threads. To avoid this, the threads using some mechanism have to request for exclusive access to the file. When one of the threads has exclusive access, no other threads of the application would be able to access the file. The threads would have to wait if they want access until the thread having access to it gives up. Any programming language that provides support for writing multi-threaded applications has to and will provide programmer an interface for various synchronization primitives. Python's standard threading module also provides a few synchronization primitives. Let us look at a few of these synchronization primitives in detail with respect to when they should be used and how. This slide defines various synchronization primitives that the Python threading module supports. Each of these primitives is implemented as a class. First one is lock. A lock is the simplest synchronization primitive. It is a state-based one and has two states, locked and unlocked. When created, a lock will be in an unlocked state, and a thread calling acquire method on the lock moves it to locked state. Execution of any other thread trying to call acquire at this time on the same lock will be blocked. Its execution will be unblocked only when any other threads call release on this lock. Next is OR lock or Re-Entrant Lock. An issue with the lock synchronization primitive is that it does not know who owns it. So, a thread that has already acquired lock blocks when it tries to call acquire on the same lock again. In such cases, we use OR lock. The next one is Semaphore. Semaphore is called by the name of bounded semaphore in Python's threading module. Semaphore is the oldest synchronization primitive and is usually used to impose conditions such as limiting the number of threads trying to access a shared resource. For example, a database. A semaphore like lock supports acquire and release, but the calling thread blocks on acquire only after a number of threads have already acquired it. Internally, Semaphore implements a counter, and when it reaches 0, the threads calling acquire are blocked until some thread holding the semaphore releases it. Event acts as a communication mechanism between threads. Threads are blocked and wait till an event is set by a different thread. We shall look into how to use this later on in this section. The last one we are going to discuss here is a condition, which is an extension to the event primitive, and it is typically used with the producer-consumer problem. In this video, we looked into the synchronization big picture, what is it and why is it actually required. Then we learned about various synchronization primitives that threading module in Python provides, along with an idea about how and when to use these primitives.